Welcome back again. This is going to be part 2 or part B of 3.7 notes. And I'm going to try to rattle through to the end with a few examples of the rest of this section. So we're going to start with problem number 8. And it says, if a ball is thrown vertically upward with a velocity of 80 feet per second, then its height after t seconds is, and they give us a function and 2 questions. So a ball from the ground is thrown up and it comes back down again, okay? And the height of the function, s of t, position, right, is 80t minus 16t squared. So it's 80t minus 16t squared. Question number 1, what is the maximum height reached by the ball? A, we're going to look for max height. Well, if you remember algebra, you might remember that, maybe you'd remember that I would just look for the vertex of this thing, and you'd be correct. We're going to use calculus, and I'm going to assume that the max height, guess what, occurs when, right at the vertex, but the velocity is neither positive, going up, nor is it negative, going down. The velocity at the top is 0, like Roadrunner and Wile E. Coyote cartoons. The guy goes up and then he comes back down again. Or am I thinking of Winnie the Pooh? Anyway, the max height occurs when the velocity function is equal to 0. Okay, so you take your position and you derive it to find velocity, and in this case I'm finding 80 minus 32t. Set it equal to 0. Solve for t. Oh man, I forgot my calculator again. 80 over 32, someone help me. I'll just leave it alone. Okay. So that ends up being an answer. If this is me old school, divide by 4, I've got 20 over 8, 10 over 4. Another name for that is 5 over 2, guess what? 2.5 seconds. That's when it occurs. The question, though, is what's the maximum height? Well, the max height would occur by, how do you find that? Do I plug it into the velocity again, 2.5? Nope, I don't, because if I plugged it in there, I just get 0, because that's where the velocity is equal to 0. We need to be plugging it into the position function, 2.5. Now I won't compute it because my calculator, my pink calculator, is missing. So I did not bring it for this series either. So what I'll say is that's going to be, in this problem I look, and yep, it's going to be so many feet is going to be the answer by plugging in 2.5. 2.5, so obviously it's equal to 80 times 2.5 minus 16 times 2.5 squared, whatever that ends up being. Use your calculator. That's part A. Part B, it says, what is the velocity of the ball when it is 96 feet above the ground on its way up and on its way down? So that's an interesting problem. In fact, it's pretty good to look at the diagram again. It's going to go up and down. The time at which it hits its max, we found out, if we're thinking about this as a time axis, and this is your height axis, call it S, well, this occurs at 2.5. But the question is, the velocity going up and down, if I draw a red line here at 96, there's going to be, no doubt, a couple of times where you are at 96 feet high. So in order to solve this problem, right, it says what's the velocity when it's 96 feet high? In order to do that, we would have to, first of all, find the time when S is 96. Now remember, the position function, T, S, time, position, But then you have a third guy, velocity. So if we could find these times, so for example, at 2.5, we have velocity is 0, and we have your answer to part A. But before that, and perhaps after that, we have a position of 96, okay, which is going to be less than the answer in part A, presumably. So what we have to do is we have to take our position function, which is this, what is it again? 80t minus 16t squared, set it equal to 96. And look what you got there. You've got a quadratic, so solve the quadratic. You know what happens when you do that? Typically you get two answers. And I'm hoping you get two positive answers. You start at 0 time, let's say, and then somewhere along the line, before you reach the top, up here, you hit 96 and then higher and then down. So guess what you can expect? You can expect from your solution, t is equal to 2 positive, and I'm sorry to cheat you. Next time I'll compute these and write out the answers for you. Time values. Now to find the velocity, what you would do is, okay, let's say that we found t1 and t2. Well, I'm going to put these in red. In your table over here, t1, 96 feet, t2, 96 feet coming down, and when you plug into velocity, so you're going to take velocity of t1, that's equal to a positive. Velocity of t2, I'm assuming, will be a negative velocity, okay? Going up, coming down. And that's a look at problem number 8, okay? Now I'm going to zip forward and look at geometry with you guys. Okay, here's a problem. This is a new thing for us. It's all new. Example, find the rate at which the area of a rectangle changes with respect to time if its width is held constant at 12 inches and its length is growing at a rate of 5 inches per second. So this one, what's going to happen is I'll work on it, then you can work on this one. I'll let you pause and work on your own. It has to do with a trapezoid, and I'll explain it to you, but I want you to pause and try. So draw yourself on this problem, a rectangle. And apparently the width is 12 inches. But the length is allowed, that's supposed to be an L, the length is allowed to change. It's changeable. What's it doing? It's changing how? Oh, I didn't read the whole thing. It's growing at a rate of, it's 5 inches per second. You know, that sounds like a rate. You know what that means? That looks like it could be a derivative, and you know what? You're right. That's kind of what it is. Okay? They want to know, though, how the area, find the rate at which the area, the question really is, how is the area changing? That is to say, you know, exactly or precisely, what's the rate at which the area is changing? Now, the length is growing at a rate of 5 inches per second, so I suppose in this direction it's getting bigger, 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 right? Okay, it's stretching outward like this, if I can get this to mark. Outward, 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 right? It's getting bigger. Okay, so how do I relate these two? Because what's happening is, you see this word seconds? Yeah, this is now, the length is actually a function of time. I don't have to write the function or anything. Actually, it's a little bit easier than that. What I want to do, though, is use a geometric constant. How are length and area of a rectangle related? That's actually pretty simple, isn't it? The area of the rectangle is equal to length times width. Okay? Now, someone told us the width is held constant at 12, so this area is really 12L. Okay? Think of area and think of L as two independent functions. A and L are two independent functions. Not independent. Why am I saying that? Just say two functions of, that's where it came from, the independent variable. Guess what it is? Time. What letter do you want to use for time? I choose T. So here it is. This is the function level. This is how they are related. But we had a rate given to us. So what we're going to do is we're going to drop down to the derivative level. And the way we do that is we assume what we're going to do is we're going to derive implicitly, believe it or not. We're going to, I'm running out of room. Derive implicitly, this is a big step, put a star there, with respect to t. Okay, so I'll put this in this other color I got. So what I write is I derive a. Derive a, it's 1, but guess what? Chain rule. dA dt is equal to 12 times dL dt. That's something new, isn't it? It gets a lot crazier in section 9. Good stuff. Okay, so we have a relationship right here of the rates of change. What are we looking for? Find the rate at which the area changes. This guy I'm circling right there, dA dt, is the rate at which the area is changing. Okay? So we can do the problem. dA dt is what we seek. That's the rate at which the area is changing with respect to time. And it's equal to 12 times the rate at which the length is changing with respect to time. And guess what? They gave it to us. It's a 5. So what's the story? 60. 60 what? 60, is it feet? Oh, it's inches. It's an area, square inches. Oh yeah, is that enough? No. Per what? Look at it, second. That's the answer, all of that. 60 square inches per second. That's how fast the area is changing with respect to time, if the length is growing at a rate of 5 inches per second. Inches for length, square inches for area. Okay. There you go. Now it's your turn. Pause it, pause it, pause it. I'll sit here. And I'm assuming you're pausing it. Now it's your turn. Okay, let's do this one. Find the rate at which the area of a trapezoid, I scribbled all over it, is changing with respect to time if the two bases are held constant at 12 and 20, and its height is increasing 2 meters per second. Well, I like to look at a picture. You worked on this. There's your picture of a trapezoid. It's mine too. One of these guys is 12, the other guy is 20, and the height is changing. And it's changing at a rate of, well, I'll write it this way. dH dt is equal to 2 meters per second. So we want the area. Well, the area relates according to this formula, 1/2 h base 1 plus base 2. So the area, notice how we have to go to the function level first. This is how they're related. Okay, still working on it. I'm going to plug in numbers I know, the 1/2, the h, and then I've got b1 and b2, which are these two added, the 20 and the 12. Well, this really simplifies to a is equal to 32. That's 16h. Still the function level. But guess what? Now we're going to take it to the derivative level, which means dA dt, very similar to the last problem, is 16 times dH dt, but I already specified to myself dH dt is 2, so we're getting 16 times 2 is 32, guess what? Square meters per second. If you got that, you did it right. Good job. Okay, moving on. I have number 18 I wanted to do together. These videos are getting long. I might be too ambitious. What's 18 about? 18 is saying, it says if a tank holds 5,000 gallons, and then there's one more after this, which is, let's do this one first, and I'll decide if I'm going to do that one next. This is number 16. Is that what I want? 16, page 234. Well, I was looking at 16 and 18, and I guess those are the ones I was looking at. Let's do 18. I might not do 16 because they're very similar. I made these notes pretty quick. So 18 says a tank holds 5,000 gallons of water, which drains from the bottom of the tank in 40 minutes. Then Torricelli's law gives the volume of the water remaining in the tank after T minutes is, so this is one where they just go, here's the volume, and it is given by, it's a 5,000 gallon or whatever tank. Yep, and we've got 1 minus 1/40th t, and the whole thing is squared, and they're saying 0 less than or equal to t. So when they say this over here, it just says the model's pretty good for that interval, but other than that, or maybe it empties after that and we're done. Yeah, it empties in 40 minutes. So this is 0, what did he say, minutes? This is important. I want to answer this absolutely perfectly well. Yeah, t is minutes, so 0 minutes to 40 minutes. By the time you get to 40, according to the word problem, it's empty. So he's given us on 18, he goes, find the rate at which the water is draining from the tank after 5, 10, and 20, and 40 minutes. At what time is the water flowing out fastest, slowest? Summarize your findings. So he's saying basically, I'll look at the first one, part A, 5 minutes. Okay, how fast is the tank? Yeah, I don't think I'll do the other one. I'll just let you think about it. How fast is that supposed to say tank draining? Okay, man, this is a thing that people kind of stumble over, but here's the story. A tank is draining. How fast? What are you talking about? What are you talking? This is something we don't think about much, but when you're in calculus and then in physics, you do. How fast is it draining? What are you talking about? It's so many somethings per minute. Okay, I'm doing pretty good. But what per minute? They're talking about gallons. Guess what? That's the story. It's so many, it's going to be, I don't know how many gallons per minute that it's draining. Okay? What does T, okay, I'll put this in red. What does T stand for right there? Time. Here's a question for you coming up. What does V stand for? And then the classroom might sit there and wait for you. You're supposed to go, volume. Good. How are we measuring volume? Is it cubic centimeters? Not in this case. It's calculated as gallons. How do I know that? Well, I don't have the book in front of you for you to see, but that's what it said. It said it drains from the bottom, blah, 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 and it says 5,000 gallons of water. That's a volume. So you got, if you want to think about it, you got time and then you got volume, okay? Now the time and volume, if you give it a time, you plug in 0, what you've got is you're starting at 5,000 gallons. And if you go all the way down to 40, okay, apparently if you plug in 40 right there, yeah, you got 0 gallons, it drained, okay? But that's not what we're interested in. That V is a capital V. It's not velocity this time. Call it volume. Now we're going to look for the rate at which the volume is changing. You know what you call that? dV, dt. That's the rate at which it's changing. All you have to do for this problem, although you might have thought, I don't know what I'm doing, it's actually not difficult. You'll get used to this. You'll just simply go, oh, here's my function. V is equal to 5,000, etc. And I want to, at this stage, this is the function level. They gave it to us. What I want to do is get to the derivative level. And what do? Well, you derive. Not just any old kind of derive, though. Well, in this case, you do derive straightforwardly. There's no mystery. There's the t in the formula right there. Okay, cool. So we derive, we go simply dv dt is equal to, wow, that's pretty fancy. You guys see this thing, you might go, how do I, chain rule. It's a chain rule problem. You see the inner and the outer. I'll do it for you. We'll say it is 5,000 times 2 stuff to the 1 to the first power times stuff derived. And the stuff inside is 1 minus 1/40th t. 1 minus 1/40th t. Okay? So we're deriving the, oh, I'm running out of room. Okay, I'm going to have to squeeze it in then. So in this case, we're getting 10,000 times 1 minus 1/40 t, almost done, to the 1, and then the derivative here is, guess what? It's a 0 minus 1/40th. It's minus 1/40th. So if I want to calculate what that with that thing, I might say I've got a negative, okay, that's going to be 1,000, this is 250 times 1 minus 1/40th t. Okay, that's your dv dt. That's how you calculate the speed at which the volume is changing. Do you notice the negative? What do you think that indicates? Well, the volume is at 5,000 and it's shrinking, so your net change is negative. You're losing volume. So this means it's decreasing right there. Decreasing volume. So to finish this problem, for part A it says at 5 minutes, let t equal 5, and you just plug in. And all A, B, C, D, all those guys, you just plug in different numbers. So you get a negative 250, and then you've got 1 minus, let's say it's 5 over 40, and calculator, and you'd say, guess what? You say gallons per minute. And that is, I think, pretty much all I want to say. Next time I'll bring a calculator. Go get one for the next video. But that, for me, covers 3.7. Any questions, of course, you know what to do. Just email me and we'll do a video on some problem, maybe a very quick one. Put it on my channel. And that's it. Okay. And, okay, where is the thing? Was I recording? Boy, yeah, I was recording. So where is the thing? I need to stop it. Okay. I know I hit the 3, 2, 1 thing. Okay. It's okay. No. Insert. And then I've got this, where are you? Is there a playback? Review? No. Please don't make me do that again. I would be sad. I could just close the app and figure out how to stop it. Okay. And I know I'm being recorded, but there's usually, I get back to this thing. This guy's in the way is the problem. Okay. I want to stop. Why are you? No. All right, no. Let's get out of this mode. Stop. Screen recording. Oh gosh, I'm gonna have to maybe just get out of this thing. There it is. Oh, there it is. You're supposed to stop. That's right. Okay, I'll figure that out. There we go.
Hello, everybody. How you doing? This is my first attempt at recording a lesson, so I hope it's going to be very.
That one. And I think I'll get him out of there. There's this one. Is it?
Okay. Hi, everybody. Like I said, we're going to work on this.
Now, where is my recording? Okay. No. Okay, there it is.